Brillouin amplifier. Optical amplifiers. An optical amplifier is a device that amplifies an optical signal directly without the need to first convert it to an electrical signal. An optical amplifier may be thought of as a laser without an optical cavity, or one in which feedback from the cavity is suppressed. Optical amplifiers are important in optical communication and laser physics. They are used as optical repeaters in the long-distance fiber optic cables which carry much of the world's telecommunication links. As the propagation of the signal over long distances may lower down the quality of the signal, so optical amplifiers are arranged in particular distances to retain the strength of the signal. In order to transmit signals over long distances, it is necessary to compensate for attenuation losses within the fiber. Initially, this was accomplished with an optoelectronic module consisting of an optical receiver, a regeneration and equalization system, and an optical transmitter to send the data. Although functional, this arrangement is limited by the optical to electrical and electrical to optical conversions. Several types of optical amplifiers have since been demonstrated to replace the electronic regeneration systems, as these systems consume a lot of power and causes in the decrease in the delay propagation of the signal, as they need to first convert the optical signal to electronic signal for the propagation and again from electrical to optical. The new systems that have been demonstrated eliminate the need for electrical to optical and optical to electrical conversions. This is one of the main reasons for the success of today's optical communication systems. Types of amplifiers. The main types of amplifiers are EDFA, Earth-Doped Fiber Amplifier, Semiconductor Optical Amplifier, which can be abbreviated as SOA, Raman Amplifier, Brillouin Fiber Amplifiers. Rare earth doped fiber amplifiers are of two types, EDFA and PDFA. EDFA can be termed as erbium doped, and PDFA can be termed as parasodium doped. EDFA works in 1500 to 1600 nanometer band. PDFA works in 1300 nanometer band. SOA works in 400 to 2000 nanometer band. Brillouin amplifiers. Brillouin amplifiers are based on a concept called Brillouin scattering, which is also known as Brillouin light scattering or BLS, named after Leon Brillouin, refers to the interaction of light with the material waves in a medium. It is mediated by the refractive index dependence on the material properties of the medium, as described in the optics. The index of refraction of a transparent material changes under deformation. The result of the interaction between the light wave and the carrier deformation wave is that a fraction of the transmitted light wave changes its momentum in preferential directions, as if by the diffraction caused by the oscillating three-dimensional diffraction grating. If the medium is solid crystal, a macromolecular chain condensate, or a viscous liquid or gas, then the low-frequency atomic chain deformation waves within the transmitting medium in the carrier could be example. For mass oscillation modules, charge displacement modules, magnetic spin oscillation modes, etc. For intense beams of light traveling in a medium or in a waveguide, such as an optical fiber, the variations in the electric field of the beam itself may induce acoustic vibrations in the medium via electroscriptonic or radiation pressure. The beam may display Brillouin scattering as a result of those vibrations, usually in the direction opposite to the incoming beam, a phenomenon known as simulated Brillouin scattering. For liquids and gases, the frequency shifts typically created are of the order 1 to 10 GHz, resulting in the wavelength shifts of 1 to 10 picometers in the visible light. Simulated Brillouin scattering is one effect by which optical phase conjugation can take place. Brillouin amplification is a distributed process and relies on the interaction of intense light with simulated acoustic photons. Depending on their frequency offset, the interference of counter-propagating pump light and signal light gives rise to moving density grating. The density grating coherently scatters pump photons into the signal beam, which thereby is amplified. A fiber Brillouin amplifier, which is FBA, has a variety of applications. It can be used as a narrowband tunable optical filter, as a demodulator, and a channel selector in wavelength division multiplexing, which is WDM systems, and also to control the group velocity of light using the Brillouin effect. In FPA, the pump wavelength is chosen such that the given signal lies within the Brillouin gain spectrum of the counter-propagating pump and thus amplifies the signal. The below shown figure is a general diagram of Brillouin amplifier. Recently, there has been much interest in controlling the group velocity of light by light and hence controlling the group delay in optical fibers using the Brillouin effect for the generation of slow light A narrow band gain spectrum is desirable, which is provided by the narrow gain spectrum associated with the process of SPS. A change in gain or loss in the medium is associated with a change in the effective refractive index, which results in a transmission in a group index. Thus, the group velocity of an optical pulse can be controlled, and hence the pulse can advance or delay as required. This effect can also be seen in the Brillouin scattering effect. For intense light beams of light, example laser, traveling in a medium or in a waveguide such as an optical fiber, the variations in the electric field of the beam itself may induce the vibrations in the medium via electronic or radiation pressure. Thus, the beam may display Brillouin scattering as a result of those vibrations, usually in the direction to the opposite of the incoming beam, a phenomenon known as simulated Brillouin scattering. The characteristics of fiber Brillouin amplification are a narrow bandwidth and a high small gain. With a bandwidth of around 10 MHz, Brillouin amplification has a built-in narrow optical and directional filter. This allows to specifically amplify, example the frequency shifted result in a return signal in fiber links, as opposite to backscatter from the outgoing signal.